Hello everybody, welcome back to another Chem Complete lecture. I am Professor Tomney, and I am going to finish the aldol condensation discussion under the Enolate lecture series today, and we are going to conclude with an intramolecular aldol condensation, which is where we are going to have one compound, an entire chain, and it will attack itself at a different location based on the aldol conditions. So we're going to take a look at that today. Okay, so let's get right into it. An intramolecular aldol is going to be a situation where you have got a molecule that undergoes an aldol condensation with itself. So let's draw an example of a molecule that could do this. One of the things you're going to have to realize, and this is going to come back up in a question that I'm going to pose later at the end of the video, is that you must have enough carbons in the carbon chain to successfully get the aldol condensation to go via an intramolecular method. Okay? In other words, you really can't be forming 3- and 4-membered rings very readily. So you have to have a high enough carbon count. 5 is usually the minimum. 5, 6, and 7 are all plausible and certainly will undergo the reaction readily. Okay, so as with most of our aldol condensations, we need our base. So we'll go ahead and provide some hydroxide. And then we'll also make sure that we provide some heat, which we're just going to represent with our triangle here. Okay, so if I take a look at this compound has 2 carbonyls, and that's going to be important because when I think about it, an aldol is going to deprotonate one set of alpha carbons on a specific aldehyde or ketone, and then if it's a self or a mixed, that enolate needs to go and attack another aldehyde or ketone in order for the entire aldol condensation to be successful. And so I have to have 2 carbonyls, 2 aldehydes or 2 ketones in order to get this reaction to go, right? Because one of them is going to be the site of the enolate formation, and the other is really going to be the electrophile or the acceptance of that enolate nucleophile at its center. So it doesn't really matter which side you pick out here, but what I do want you to realize is that we need to target these carbons out here. And the reason that I say that is because, again, if you take a look in here, and a lot of students will ask this, why can we not pull from these carbons right here? Well, the answer is, if we were to form an enolate out of, let's say, this carbon right here, then it would have 1, 2, 3 carbons, right? If it were to come in to attack that carbonyl. So you'd be looking at a 3-membered ring with a carbonyl substituent and a methyl substituent. That is not going to be a stable compound, and therefore the chance of that actually proceeding forward or going in that direction is very, very small. You're not going to get a whole lot of that product, and even if you did, it's not going to be around for a very long time because it's got severe angle strain when you're compressing those angles to 60 degrees. So if we want to proceed forward, we're going to pick one of these. We'll just go ahead and say that we form the enolate right here on this edge. Okay, so this hydroxide is going to come. It's going to take one of these hydrogens. The electrons from one of those hydrogens will go to the carbon here, and we will start by forming our enolate. Okay, so one of the things that's also going to be important when we're doing this, and you may have seen this when you're doing other sorts of reactions, especially like conjugated diene reactions, like a Diels-Alder reaction. But that is going to be to count carbons so that we don't lose track of what goes where when we're getting ready to form this cyclic compound. Okay, so here's our enolate. We've got a lone pair there now that would obviously be in resonance with that oxygen, which would be its major form. And now the enolate is ready to attack the other carbonyl on the chain. Okay, so mechanistically, we can do that by simply drawing the carbon here, and it's really its lone pair that's doing this, right? Coming in and attacking this carbon for the carbonyl right here, and then this would also open up. Now this, and I'm going to highlight it in a different color, is where I want you to pay attention. So when we take a look at this, as far as carbon count is concerned, we are going to have 1, 2, 3, 4, 5. So it's a 5-membered ring. If I count the enolate being carbon 1, and then moving all the way over to the site of attack, the site of attack is carbon number 5. And so that means that I would expect a 5-membered ring to come out of this. And if I take a look at this, okay, it will also have a carbonyl in position 2, and then it will have in position 5, which will just start as the top of the ring, it will have this carbonyl with this oxygen, okay? So let's figure all this out. I'm going to need a 5-membered ring. So the first thing that I'll do is I'll simply draw my cyclopentane, okay? And now with this 5-membered ring, I have to take a look at what I want in each position. So it doesn't really matter which one you call position 5 or 1, as long as once you pick a spot, you move forward from there. Okay, so I'm going to call this position right here at the top of the ring position 5, and we're going to move from there. So at position 5, I can expect that this position, this carbon right here at the top of the ring, is this carbon right here, this carbonyl. So that oxygen should be present in an O-, right? It's going to be in its tetrahedral intermediate state. It definitely will not be in that carbonyl state. And then I also have the methyl. So don't forget that this methyl is attached to that carbonyl. And so I need to go ahead and also make sure that I've got my CH3 added here as well. Okay, so that can be position 5. That means that what attacked here, whether I'm looking at this end or this end, is position 1. So I'll go to the right and I'll say that this is really going to be carbon 1 right here, right? Because carbon 1 formed a bond with carbon 5. And so they have to share a direct set of electrons through a covalent bond, and that's going to be this bond right here that is part of the ring structure. Okay, so I will call that my CH2 enolate, which means then this now has to be carbon 2. At the bottom of this ring right here, this is carbon 2, and that carbon has a carbonyl. And it's just a carbonyl. It hasn't opened up or anything because there's 2, right? So this would be 3, and this would be 4, and there you go, we're back to 5. So everything here seems to make sense, right? This is a CH2 in position 1, a carbonyl, a CH2, and then finally this opened part right here. So this is good. We've got what we need for our intermediate. Now, as an aldol reaction would proceed, we would expect the water to be deprotonated in order to provide the alcohol group, and then that functional group, because we did mention heat, will dehydrate into the final product. Okay, so let's see what we've got right here. Okay, for this, we're going to have the carbonyl down here. We would have the OH here, and we would still have our methyl group up here. And at this point, we are now going to, I'm going to go ahead and I'm going to explicitly draw one of the 2 hydrogens on this CH2 because I'm going to need it for the dehydration, right? So this hydroxide, which I just regenerated from the water in the previous step, can come down. It can grab one of these protons, and then this set of electrons right here can go into forming an alkene, which will be present right between those 2 carbons, carbon 1 and 5. And then this hydroxide will leave, just like we've seen in the previous examples. And if you don't know what I'm talking about, go back and check out the introduction to aldols with the self-aldol condensation and the mixed aldol condensations. We've kind of gone through this methodology and mechanistic chemistry here. Okay, so what do I get as a result? I get a 5-membered ring that's got some conjugation going on, p orbital overlap. Okay, and so I have my 5-membered ring, I have my carbonyl present, and then right here I would have a double bond, and that methyl is still present up at the top, right? Because nothing happened to the methyl, it was the OH group that was the leaving group. And so this would be the correct final answer here, and that takes you through an intramolecular aldol. So again, the key concepts here. Number one, you have to have 2 carbonyls in this chain. If you only have one, it's got to be a self, or if you have another compound, then it can be a mixed aldol. As long as you've got the 2 carbonyls, the next thing you have to realize is that there has to be an appropriate amount of carbons or space between them in order to get an enolate that could attack to create a 5, a 6, a 7-membered ring. You want to stay away from the 3 and 4-membered rings. They're just not really plausible as far as stability is concerned. Okay, and then the last thing that you want to realize is count your carbons. Even if you're pretty sure, I still make mistakes, and I've been teaching this for almost 20 years. Count your carbons because it will help you keep track of what goes where. Even if you say, I know it's a 5-membered ring, do you know where the carbonyl is? Do you know where the OH group is going to be? Do you know where the alkene is going to form? It very much helps if you kind of methodically work this out stepwise like this, okay? So that is all I have as far as intramolecular aldols. And we are going to see a similar pattern emerge when we look at the next subject, which will be Claisen condensation. So you're going to see we can do a self-Claisen, a mixed Claisen, and then there is a specific name, the Dieckmann reaction, that will be an intramolecular Claisen. So go back and rewatch this video if you don't quite understand it, because it is going to be important moving forward. We are going to discuss more intramolecular condensation reactions. Okay, so like, comment, subscribe, all that good stuff. If you subscribe, you'll be up to date throughout the school year whenever I release content. And of course, it always helps in terms of showing us support. If you want to find other ways to support the channel, we do have a website at chemcomplete.com. I have all sorts of guides there that are very affordable in the $5 to $10 range, how to pass organic chemistry and prepare. I've got one on NMR spectroscopy and how to solve unknowns, all sorts of stuff. And then, of course, YouTube has now added the thanks button, which is essentially a super chat type of function for a video. So you can always donate if you just appreciated the video and you want to drop $1 or $2. That helps support us too. And of course, the biggest form of support is continuing to learn through ChemComplete for all of your chemistry needs. Thanks for learning with me today, and I will see you guys in the next one.